sodium ion, and then this one here, it's actually C to deprotonate. Deprotonate. All right, so again, same sort of a mechanism as we've seen with the first three. We generate a strong electrophile here on the top. Here it happens to be a carbocation. And then the reaction, just like what we've seen before. So it's going to react with our aromatic system, form the bond between happens to be benzene and the electrophile here, forming this resonance stabilized intermediate, which we're not drawing the resonance structures, but it is resonance stabilized. And then we deprotonate to regenerate the aromatic system. Now, a couple of things about this reaction, and this one, it could be very powerful because you're forming a carbon-carbon bond, and we've been emphasizing it throughout our time this summer. However, a challenge here is that you generate a carbocation. And so remember back from carbocation, what I meant to say is remember back from organic 1, that whenever one generates a carbocation, there's lots of things you have to be on the lookout for. And so, as Abbas asked, is this the only one that had alkyl groups? There, the answer is also yes and no. So it's yes, that directly add an alkyl group. However, we're going to see a two-step reaction that can be used to add alkyl groups as well. So we're getting to that one here in a second. So this one, because it's a carbocation, it works best for secondary and tertiary carbocations. You might imagine taking this species here, same benzene, and let's add this tert-butyl chloride and AlCl3. We won't draw the mechanism. I can draw benzene a little bit better than that, I think. No, maybe not. I guess. All right, we'll go with that. We're going to add a tert-butyl group. So that's all good. And it does work for primary alkyl halides. So we can take benzene again, and let's put the chloro here, this ethyl chloride, AlCl3. And you can introduce an ethyl group. Why I'm bringing this up is it seems kind of unusual. Remember back from organic 1 that forming a carbocation as primary, we have a carbocation here, is highly unfavorable. And I'm just going to scroll up for a second. We're not going to spend much time on the details of that, but here in the top, I'm going to circle something kind of in the top middle. This reaction seems to show things that are carbocation-like in chemistry, but maybe in the primary case here, ignore this alkyl group here, it doesn't completely form a true carbocation. It might still be associated with this aluminum species. So I'm thinking back about organic 1, thinking how, why would this actually work when you're forming a primary carbocation? There's another complexity here, is that we're going to treat it as forming up here in the top right, this formal carbocation, but in reality, sometimes maybe it actually doesn't. So maybe in the secondary and tertiary case, you actually form this true carbocation, but with primary alkyl halides, you have something that's still more coordinated with the aluminum. So I know those are a lot of details. I'm trying to put it in context of some of the chemistry that we've seen earlier. However, along those lines, let's scroll up here for a minute. Let's consider this reaction. Let's take benzene again, and let's treat it with this primary alkyl chloride in the presence of aluminum trichloride, and you actually end up with two products. You end up with this plus this. So two alkyl substituted benzenes, and this one is the major product, really small, and that one happens to be the minor product. So we want to think about what's a possible mechanism. And we'll make a simplification compared to what we just saw earlier. Let's take our alkyl chloride and aluminum trichloride. Normally I guess I've been writing more spread out. So same idea. Let's have lone pair of electrons and a Lewis acid-base reaction, form a Lewis acid-base complex. Now, I just went through all of this stuff about, maybe it's a carbocation, maybe it's not for a primary case. Here, for the purposes of illustration, let's assume that this is going to leave and form a primary carbocation. And that's to simplify. Let's see what that forms. So we'd end up with not a triangle, not sure where that came from, but 1, 2, 3, 4 carbons, the carbocation, plus I'll collapse it down over here, AlCl4 minus. Now, if that's the case, this one here is a primary carbocation. And I bring this up because remember back in the good old days of organic 1, whenever you form a carbocation, you need to be on the lookout for a rearrangement. Am I able to form a more substituted / more stable carbocation? And typically we saw that if you have a hydride or a methyl group that can shift and form a more stable carbocation, that will happen. So in this particular case, let's have a hydride shift over. And see what that gives us. So now we have carbocation here, and it's actually a secondary carbocation. So that's more stable. Now I can imagine what ends up happening if the benzene ring nucleophilically attacks here, our primary carbocation, or attacks our secondary carbocation. That'll lead to our two products. So the first one, let's not draw the whole mechanism because that's what we've already seen. This would come from the primary carbocation. And this product here, this one up here in the upper right, is attack at this carbon here, which is the secondary carbocation. So this would be the product resulting from the secondary carbocation. So in this Friedhoff-Crafts reaction, we can have rearrangements occurring because we're going through a carbocation mechanism. So that's something always to be on the lookout for. I kind of feel bad sometimes when we're presenting this in the class because this is a great reaction, but it does have a lot of limitations. There are a lot of other strengths to it, but we'll focus on a few limitations here. So one, that does not work with things like an aryl chloride or a vinyl chloride. And this is a good thing to bring up here because remember back also in OChem 1 that forming a carbocation at this particular position of the aromatic system, notice we're not breaking aromaticity, we just had a carbocation here or on the carbon of the double bond, that's highly unfavorable on that sp2 hybridized carbon here to form a carbocation. And since we're going through a carbocation mechanism, that's unfavorable. Number two is it does not work with deactivated systems. And that's going to be the second part of our discussion today. So let's call it a ring. So if we have a highly electron withdrawing group, nitro is a classic example of that, and we wanted to add this alkyl chloride, AlCl3, it would have no reaction. So it's limited in terms of the sorts of aromatic systems that you can use. On the other side is it often results in what's known as polyalkylation. Alkylation. Let me write that neater if I may. It's about the same. So that if we take this benzene, some crooked structure that's drawn here, and now we use that tert-butyl compound that we used earlier, what ends up happening, and I'll get to your question in a second here, Stage. What ends up happening is that when you put on this alkyl group, and this also somewhat gets to the question, is that we're going to see in a few minutes what are known as activating and deactivating groups. And an activating group speeds up the reaction. It actually donates electron density into the benzene ring. And I'm just going to assert for a minute here that this alkyl group, because the carbons are electron donating, actually activates this ring to make it more reactive. So what happens a lot of times is that you've ended up making an aromatic system that's even more reactive, so the reaction happens again. You end up with, and we'll keep them apart from each other, polyalkylation, meaning the reaction happens multiple times, like polymer, so multiple units. So at times it's hard to stop the reaction at, say, just putting on one alkyl group, and you'll end up with more than one alkyl group. Now, I just threw this deactivated ring term out here without explaining it, but what we're going to see here in a couple of minutes as well is that when you have groups that are withdrawing electron density from the ring, so this nitro group is pulling electron density away from the ring, it's going to make this benzene here, really, it's less nucleophilic, or it's deactivating it to act as a nucleophile, because we want to use electron density here to act as a nucleophile. So if you have stuff pulling electron density away, say by induction, it's going to make this ring less reactive, and the jargon for that is to deactivate it. And so we'll see some more examples, excellent, of these activating and deactivating groups. So I know we're going through this quickly here. I ask if we can just hang in there for the one last reaction, and then we'll pause for a few minutes. But I think hopefully if it's okay to keep up with the parallel structure, we'll go through the last one here.